Coming up on StarTalk Special Edition, we're going to do a version of Cosmic Queries, but with the help of Charles Liu, everyone's geek in chief. And one of the questions posed is, who does he call when he doesn't have an answer? You'll learn that and more coming up on StarTalk. Welcome to StarTalk, your place in the universe where science and pop culture collide. StarTalk begins right now. This is StarTalk Special Edition. Neil deGrasse Tyson here, your personal astrophysicist. And as usual for special editions, we've got Gary O'Reilly. Gary.
Hey, Neil.
If you didn't know, former soccer pro, a football pro, I guess they say that over in the UK, a turned announcer because he's retired. And we get to use a bit of him for our talk. So thank you, dude. And recently married.
Yes.
Congratulations.
Happily married. Who knew it would last this long?
What, 6 months?
Not even that.
Congratulations, the first 6 months of marriage.
Thank you.
And Chucky baby.
Hey, what's happening, Neil?
I feel bad because we're checking in with you. You're doing a comedy stint in Aruba.
That's right.
Right now.
So
you're on this instead of being on the beach. So we'll try to make this quick for you.
I was on the beach and left the beach.
Don't rub it in. Let me say. No, don't you have to make a thing out of it.
Literally, I was in the Caribbean, swimming around just 20 minutes ago.
Okay.
Came up here and said, okay, let me get back to the room and set up and do this.
So what we're going to do is we're going to have a kind of a Cosmic Queries, but like a special edition of Cosmic Queries. And whenever we're in kind of grab bag mode, I need some help. And you know who we go to for that, of course. Charles Liu. Charles, welcome back.
Hey.
Yay.
Hi, Gary. Hey, Chuck. Great to see you all. I was not on the beach just now, so
not on the
I'm particularly happy to be here with you all. Hey, Chuck, we're of course all envious.
So Gary, you brought in the questions and you curated the questions.
Yeah.
We had more. You told me we had more than 100 questions on the solicitation.
Yeah, and apologies up front for those questions we couldn't get to. We only going to get about an hour's worth of this show, so we had to flash through. They're all from our Patreon patrons, so thank you so much for your curiosity. Let's start with Gina Martin, shall we?
Mm-hmm.
Since time, as we know, moves in a straight line, can we consider time being one-dimensional from our perspective? That being said, what would it look like if time had 3 dimensions just like space? And is that even possible?
Whoa.
Well,
Okay, Charles, I'm glad you're here, Charles.
We'll start with an easy one, right?
Yeah.
The reality is that we can indeed, thank you for your question, think of time as a dimension. In fact, the Rolling Stones sang a song about that. Time is a dimension, right? But yes, the general relativistic assessment of space-time is
Einstein general relativity.
Yes, Einstein general relativity describes space and time as 3 dimensions of space and 1 dimension of time. Now, there have been some work over the years, theoretically. What if there were more than 1 dimension of time? And what happens is complicated, as you might imagine. But the most significant
so that's the answer. It's complicated. Next question.
Yes. Well, the most significant effect we would have in our lives is on causality, right? Neil, as you know, we think of time passing as stuff in the past affecting what happens in the present and the future, but not the other way around, right? If you have 3 dimensions of time and you can travel both forward and backward, also left and right and up and down in time, then you don't know what the past is by definition. You have to change your concept of what causes what, because you can be dancing back and forth in a different dimension, and something that you thought was in the past might actually loop around in a say grand view and wind up in our future.
When you say grand view, you mean a view from outside of those 3 dimensions?
Yes, that's right.
Right. You'd have to be above. You have to be above.
Yeah, above
down.
And beyond that whole set of coordinate system.
Right. String theory, you've seen that happen all the time too. But imagine kicking a football, right, a second ago, but actually having kicked that football a second ago in 1 dimension of time, but kicking the football 5 seconds from now in a second dimension of time, and kicking it at the precise moment now in the third dimension of time.
Wait.
Where's
Is
that
there a
ball gonna
dimension
go?
is there a dimension where you don't kick the football?
Not in this configuration.
That's called the Charlie Brown dimension.
I forgot about that dimension.
Yeah, that's the Charlie Brown
So,
dimension.
so
That's the
Charles,
dimension.
is it just humans that see time as a straight line? Other beings in other galaxies are perceiving in a very different manner.
Great question. At the moment, since we haven't found other beings in other dimensions or other parts of the universe, we don't know what their brains are structured on. But the universe as a whole has a causality to it. In other words, all of the universe as we conceive of it in Einstein's spacetime only has one dimension of time. If there are other dimensions of time that we somehow can't perceive, but other creatures can perceive, and as a result, the universe's causality proceeds differently from what we see, then you build up those cool science fiction ideas like Arrival, for example, which that was the Amy Adams movie a few years back, I think.
Yeah, not the Charlie Sheen Arrival from a few decades ago, but the one where they have the linguist and the physicist,
right?
Instead of the astrobiologist and the cryptographer.
Yes, that one. Where the premise was, if you know your future, would you want to experience it anyway? Right.
Oh.
Right. Yeah. And the answer is yes. I want to know my future.
And then you want to live it? I mean, even if you knew all the good and the bad.
See, but here's the thing is, you wouldn't live it. No one's going to live the future that they know. But you may ultimately cause it by not living.
Oh.
But no one is going to live the future that they already know. So
no, Chuck,
that's the problem.
You're completely right if time is one dimensional.
If
time is 2 or 3 dimensional, then you don't. Maybe that's not right.
See? There you go. Right.
Good question.
All right. Okay. Loved it. Okay, Chuck, you got a question?
Yeah, here we go. This is Morgan Fisher. Morgan Fisher says, Doctors Tyson and Lou, it's Morgan from Waterloo, Ontario of the Perimeter Institute.
The Perimeter Institute. Very nice.
She says, I've wondered about this since first hearing of the LIGO experiments. It is said that colliding black holes create ripples in space-time. But what's the medium? There's no air. There's no water. It's a perfect vacuum. So what's actually doing the rippling? And I think she answered the question in the question.
Let me lead off by saying the Perimeter Institute is a place of study where people are asking questions that kind of sit at the perimeter of established and accepted thinking in physics, math, philosophy, this sort of thing. And so it's an audacious construct among institutions that are out there. And if there's any weird, wild, wacky idea that turns out to be true, it's more likely to come from those kinds of think tanks rather than from those in the establishment. But Charles, why don't you take a gander at this answer?
Well, Morgan, you have put your finger right on the concept of the general theory of relativity.
Exactly.
Space itself is a medium. What Einstein explained...
Empty space.
Empty space. Yeah.
What Einstein explained was that our conception of space being just vacuum or nothingness was incomplete. Rather, we should think of space as this sort of giant, either a rubbery sheet or a flexible sort of jello that we live in that can be bent and twisted and torn and so forth. So
Jello.
Space is a lot like jello. Albert Einstein showed that space is a lot like jello. You know, I mean, it's a children's song. Yeah.
Well, now, what part of the universe has the pineapple chunks in it?
Earth.
Okay.
You see the pineapple chunks that sit in your jello mold, right? Some of you may have had that and things.
And the grapes. Yeah, that's the 1960s section of the jello mold.
The things that are floating in it are indeed mass. Massive particles and objects or agglomerations of mass, such as planets, stars, galaxies, and so forth. And those blobs cause an irritation to that otherwise beautiful, perfect jello. It It's an irritant that winds up causing space-time to curl in upon itself. And that's what gravity is. It's the curvature of space-time.
What I like about the Jell-O is you can send a ripple from one part of the Jell-O, and that ripple will propagate out as a Jell-O jiggle.
That's right.
And jiggle its way across the pineapple bits. And if you're in the pineapple, you'll feel a little jiggle as the wave moves across.
Absolutely.
Right.
So good job, Morgan. You absolutely understand the point that Einstein was trying to make when he developed the general theory of relativity.
Yeah, but I don't know if that's a satisfying answer to Morgan, because what you're saying is the vacuum is a thing, so get over it. That's really, I just gave the short version of your answer.
Well, I didn't use get over it. I would say revel in it.
Okay.
The nothingness is the thing, so revel in it. Enjoy it. Make jiggles in it so that you can send it, off to the next part of the Jell-O bowl.
All right.
Okay, let's embrace the nothingness. Right, next up, Dennis from Indiana. Black holes. Are we sure Hawking radiation is coming from the inside of the black hole? Or is it just from around the event horizon? Has an observation ever been made of a black hole dying or disappearing, stellar mass or otherwise? Gentlemen.
I'm going to reshape that question and hand it back over to Charles. So we know that Hawking radiation is birthed just outside of the event horizon. We know this, okay? That's how the calculations unfold. However, somehow that means the mass inside the event horizon drops. And I want to ask Charles Liu, how does the inside of the event horizon have any clue what just happened outside of the event horizon? And that's a reshaping, but a tuning of that question.
That is a great question, and the answer still is we don't know. You see,
okay, next question.
Okay.
But the idea is that we know, mathematically speaking, Hawking radiation comes out of any object. It doesn't have to be just a black hole. It just comes off of any object that has mass, except that from a black hole, that's the only thing that can come out of the event horizon. And that's sort of the strange part of Hawking radiation. It's not that it is unique to black holes, but we couldn't measure it if coming off of me, for example, or of Chuck or the Caribbean, as much as we'd like to. It's a lovely place to be, but it's very, very slow and very, very small. What happens to create that Hawking radiation is still a mystery. Hawking himself didn't understand. Now, you know, Neil, right, about how people often describe Hawking radiation as maybe like a particle getting close to the event horizon inside and then splitting off production into a particle and antiparticle, and then the particle escapes the event horizon, so on and so on. That is pure speculation. That works mathematically, but physically, it has never been shown, and it's actually a little bit problematic theoretically.
But I'm good with it though. I'm good with if Hawking said it. I'm good.
Well,
first of all, you're talking about the evaporation of something like the Mojave Desert, 1/2 grain of sand at a time.
That's right.
Which is
very,
insane.
Very slow. That's right.
Very, very, very slow.
But answer my question. If a black hole can evaporate completely, how does the inside of the event horizon know what happened on the outside? Or is the event horizon just a convenience for us to describe the edge, but really the black hole and its gravity field, the black hole doesn't doesn't have an edge, that it's wherever the gravity field is, and the gravity field collectively is the black hole, and the Hawking radiation comes out of the gravity field, therefore it loses mass.
This is another frontier question. A paper was published about 20 years ago that suggested that mathematically, Hawking radiation could be described as quantum tunneling, a thing where violating what we normally think of as the boundaries of any given object, you can temporarily, every once in a while, get a little bit of stuff.
That's another way to think
past
about
the boundary. Right. And it's mathematically valid. So if it is a quantum tunneling process, then just as you said, Neil, that
it's escaping.
edge is a shimmering surface from which things can escape.
It's a fuzzy
We
surface
still don't
for
know.
it.
That's right. There's
Yeah,
a lot more that needs to be done to
I would
understand.
take a minute just to describe quantum mechanical tunneling, then we'll go to the next question, right?
Sure.
So if you're trying to get to some destination in front of you and there's a hill there, you got to climb up the hill and then climb down the other side. And that's a pain in the ass. And maybe you don't have the energy to do that, so you never get there. In quantum physics, you're a particle and there's a barrier there. You're not just a particle, you're also a wave. And that wave occupies space. And part of your wave exists on the other side of that hill. And so there's a chance you could disappear from where you are and reappear still within your own wave pattern on the other side of that hill. And when that happens, it's called tunneling. And it did not actually have to go over the hill and come down the other side to get there. And when it happens instantaneously. There's no time travel for it. The wave for the particle, as we say, collapses and the particle exists outside of the barrier. Outside.
Now, does this remain true even for Jack and Jill particles?
Who went up the hill and came down?
Jack and Jill didn't go up the hill to fetch the pail of water. They just tunneled right through it.
It just
got
reappeared on the other
there
side,
you go.
inside of their own wave.
Hello, I'm Alexander Harvey, and I support StarTalk on Patreon. This is StarTalk with Dr. Neil deGrasse Tyson.
All right, who's next up? Is it Chuck?
Gavin Bamber. And Gavin Bamber says, hello from North Vancouver. Please visit. And then he says, in lieu of a nice question, I kneeled down and asked the following.
Man. 3 puns in a single sentence. Well done. Now I really have to go to Vancouver.
How many black holes are there in our galaxy compared to the number of stars? Is there a fixed ratio, or is this just a random ratio?
Ooh.
So, yeah. Well, we know. And do you count the one at the center of our galaxy?
That's just one.
Do you count?
One.
Yeah. Okay.
Yeah,
so
yeah.
that does count.
Well, this is a
So
great
I'd like to
question.
compare our estimates because both Charles and I have extensive research background in the answer to that question, but we might not end up giving the same answer. So Charles, let me hear your answer.
Oh, okay. Here's my take. Black holes are formed only by the most massive stars dying. And so for every massive star that can create a black hole at the end of its main sequence lifetime, there are millions of other stars that cannot do that. So the maximum amount of black hole to regular star ratio is sort of millions to one. But then black holes, it has now been shown, thanks to LIGO and others, that black holes can coalesce and combine and create larger black holes. So that total amount can only shrink as you continue to go forward. As big stars blow up, 1 in a million or less, new black holes can be formed. But then as they coalesce, they drop. I don't know what the exact mathematical ratio of all that is, but I'm guessing that it's millions to one or even more rare black holes to regular stars. Neil, what's your take?
Okay, I would say it's not as rare as you're suggesting because it's just a simple integration of the initial mass function of stars. And you just find out the stars that are more massive than 8 or 10 solar masses, whatever the threshold we agree that would be. What fraction of all stars in the galaxy are born with a mass higher than that? I think it's not 1 in a million. And the reason why I say that is we have clusters of stars that don't have a million stars in them, but have a high mass star that would die that way. Maybe 100,000 stars or 10,000 to 100. So I would say 1 out of every 100,000 stars in the galaxy, stellar objects in the galaxy, is a black hole as the consequence of the death of this process. Because when stars are made, they're made in what's a group of star? A pod? Or should we invent the name
a
of a group
cluster? an association.
Close. Yeah, that's so boring. I want like a zoological.
A litter.
A litter of, thank you. A litter of stars born out of a gas cloud. We know that the low mass ones, many more stars are made that are low mass that are high mass. It's rarer and rarer and rarer. Interestingly, if you take a sheet of glass and drop it on the ground and it shatters, there will be more small parts than big parts. Okay? A lot of things land this way.
The initial glass function.
The initial glue. Very good. Very good.
No, you're so right, yeah.
So, Charles, I'm saying I bet it's more like 1 in 100,000, not 1 in millions.
That's quite a discrepancy between 1 in a million and 1 in 100,000.
But between astronomers, that's like the same number. We don't,
exactly.
Yeah, we don't.
They don't care. They don't care.
You ain't doing my tax.
Yeah.
Seriously, you're not doing my tax.
Here's what I want to know: when a stellar nursery produces a litter of stars, does the galaxy then hound the rest of the galaxies to take one of them?
Yeah.
Like, hey, they're so cute. You're gonna love it.
We just need some galactic nannies to take care of them
Yeah,
at the same time.
Exactly.
Yeah.
Okay,
All
so
right.
Charles, do you see my reasoning there?
I do. I ask then, do you take into account very low mass stars and brown dwarfs? Because if you think a typical salpeter initial mass function, right?
Yeah.
10 solar masses, every star that's 10 times the mass of the sun, there are 100 or more stars, 200 or more stars that are the mass of our sun. And then,
But those brown dwarfs, isn't another term for brown dwarf a failed star? Yeah.
or an
So you can't
overachieving
really
planet, right?
Right. There you go.
Yeah, so
Right.
staying. Oh, so what Wall was saying is
Right.
that the initial mass function of stars would include these things that are not stars that would come in even higher numbers than the lowest mass stars.
Right.
So Charles is just being sort of complete in the mathematics there.
If you're
That's
going
all.
all the way down to the borderline of brown dwarfs, right? Then for every star that can produce a black hole, there are millions of objects
other
that
stuff
cannot.
out there.
Of objects.
That's
Other
right.
objects. There
That's
you
right.
go.
Other objects.
And
There we can
initial
agree.
That.
Yeah, and the initial mass function of brown dwarfs appears to be flatter than that of regular stars that can have nuclear fusion. So, yeah.
Okay, so
this is
Gary,
an
we'll
open
both
question.
do your taxes coming up, okay?
And you can take the average of our answer, and then you'll be bang on. Yeah.
I'm sure the IRS are going to love that.
Yeah, I was going to say you could take the average of the answers, and you'll still go to jail.
Yeah. I'll stick with someone else.
Gary, give me another one.
Cameron Berg says, hello, Dr. Tyson, Lou, and of course, Chuck himself, hailing from Salt Lake City. And his question is it possible that what we call matter and energy since the Big Bang have left a lasting or ghost effect in the fabric of space-time, and dark energy continues to grow because the effect keeps building as matter moves and expands into new space? So there we go. Cameron Berg's question.
Is
Good
he saying,
question.
Charles, do you think he's saying that is the dark matter the absence of the matter that has moved from its location? Is this?
I feel like if I were to interpret this question more, it would be sort of like, is the residual effect of the Big Bang what the dark energy is as it fills space?
Wait, dark
and time?
energy or dark matter, did they say?
Dark energy.
He said dark energy.
Energy.
Oh,
Right.
oh.
And so my response to that, right, and Neil, you can correct me if you disagree, that
That
dark
won't happen.
energy, you're very sweet. A dark energy has been shown clearly not to be the result
Right.
of matter and energy as we understand it, including dark matter. All the
Right.
contents of the universe cannot explain how the universe itself is expanding in a way that is counter to that material. So that
Especially
was a
given the
different
fact
thing.
that dark energy is operating in the opposite sense, that energy, matter, and dark matter would have the universe behave.
That's right.
So
the
it's hard to
larger-
explain one thing with the other when they are complete opposite in what their forces are.
Right. The larger the universe gets, the more dark energy there has to be in the current formulation. And that just means that anything that's left over from what exists in the current universe cannot power that additional dark energy creation.
Yeah. So deal with it.
Wow.
Neil, you are harsh today.
I know.
Like,
I know.
"Dude,
I'm
move
getting
on."
old and tired, and I'm on the porch on my rocking chair. I'm
Ah.
feeling it. I'm older than all y'all, so I get to behave this way.
Nah.
No excuse.
All right, Chuck, what you got?
So this is Emil Forsblad, who says,
Wait, what?
Hey, it's
Forsblad.
Forsblad.
Emil.
Emil Forsblad, who says, Hey, Emil from the San Francisco Bay Area, wondering about the potential measurement of consciousness.
Ooh.
I believe what we call consciousness is an energy or a quantum equivalent that emerges, grows, expands, converts like other forms of energy or / matter. It seems that as the universe expands, consciousness is emergent as a natural result of the separation of all matter from its source over time. We likely need something to measure emergent consciousness if it exists as some fundamental energy. What would we use to measure other forms of energy like consciousness?
Ooh.
Wow.
Honestly, your consciousness is not. Your consciousness right now is electrical.
Wait, Chuck, that's the wrong reply. It's, what are you smoking?
I don't know. No.
Chuck missed that one. I got low-hanging fruit right there.
No. Like, Emil, many people agree with your belief. Believe as you do that consciousness must be something physical. And
it's a thing.
Different.
It's a thing.
Yeah.
Right. There is not yet any scientific evidence to confirm that. If there were some way to measure it, we'd be working on it right now. In fact,
where does it come from?
Right. There have been
Where's
studies.
it come from, though?
Right. There have been studies, for example, where they tried to measure the mass of a soul or a consciousness based on the mass of your body or your brain before an event and after an event in terms of consciousness or unconsciousness. And there just hasn't been anything yet. So that said, we should consider the possibility, the more likely possibility, that consciousness is not an emergent form of new energy, but an emergent form of information or organization of well-known existing energy that somehow transcends just the motion of photons back and forth in our brains. Neil, you probably have much more understanding about consciousness.
Well, I like what you said there, but I want to add to it.
Yeah.
Something that I think it was Brian Greene. We were having lunch a couple of months ago. This came up in conversation, and it's stuck with me ever since. All right. You want consciousness to have some energy field that might be shared among people. By the way, in physics, anytime something happened that we couldn't explain, we investigated it, found out what caused it, exploited it, and then went to the bank with it. So go back in the middle of the 19th century, there's Faraday, who puts a wire through a magnetic field, and there's a meter over on the side connected to that wire, and it moves. And, how does that happen? It's like, today, which seems so trivial, back then was an amazing, you do this over here, and that happens over there. What did that? And then you find out there's current, there's something called an electron, which hadn't been discovered yet, and all kinds of discoveries come out of this. Anytime any of us in the physical sciences confronted something that was behaving in a way that we didn't know or know the cause of, we investigated it, okay? And so, on a tabletop today, there's nothing left that is happening where we're saying we don't know what's happening. Not on a table, maybe in a particle accelerator, but on a tabletop, no. Your consciousness counts as a tabletop. Everybody's sitting around the table. So now, here's the mind-blowing part. When LIGO measures the gravitational wave washing over the detector, it is measuring the movement. It is measuring matter at the level of 1/20th the diameter of a proton. And that is this wave that has moved through the universe for 1 billion years. If there was something going on in the universe affecting matter, we would see it in that experiment. If there was some mysterious other thing, somebody has a sixth sense and they have a energy field and they got it. It would show up in those data, but it doesn't. So I think we can speak with confidence that there's not some mysterious mind energy that's permeating space that science has yet to discover. Because I'll tell you what, if it was shaking up that atom, we'd have to account for that before we measured the gravitational wave. And there was nothing there left to encounter. And Charles, do you know I visited the LIGO in Louisiana? Okay.
Wonderful. Oh, what a great facility that must be.
And I happened to be there like 3 weeks before they made the announcement, and everybody was like hush lip because they thought I would just run to social media and say, no, I'm way more responsible than that. But anyhow, so when I watched the kind of stuff that they had to subtract out of their signal, with somebody walking on the ground 100 meters away, there they are right there. Yep. A car a mile away. There's an experiment where they measure the gravitational constant. It's not LIGO, another one. Okay, so they got these torsion beams and things measuring, which is a very hard thing to measure.
Yeah,
you realize there's a mound near that facility where if it had just rained, that mound is waterlogged, and they can detect the extra gravity of the water that's in the water and in the soil.
Yeah, it's pretty amazing.
So anyway, that's my long discussion to say, I agree with you, Charles. It's not a new kind of energy or force. It's familiar energy configuring itself in such a way to give us a perception of reality that we call consciousness.
So Neil, do we measure consciousness as positive and negative, bearing in mind the thought process you have?
It depends on if you're into positivity or negativity. I don't
Figure that.
Haters will be haters. That's negative.
That's right. Yeah. All I know is my soul did weigh 21 grams, but then I went to Soul Cycle and got it down to about 8.
Hello.
Nice job.
All right, let's get our next one up here. This is from Boutayeb Badawi, and he is from Nice in the south of France.
Boutayeb, nice. That brings back memories.
All right,
the surname Boutayeb. Yeah, I'll tell you.
No. Boutayeb is, I believe, the first name, and the family name is Badawi. If I've pronounced that incorrectly, my apologies.
Wait. Is this a European guest?
Yes, from Nice.
Then they probably put their surname first, right?
All right. Boutayeb?
Yeah. He's a Brit. What does he know, Charles?
Exactly.
No.
Yeah. I'll tell you, I'm no longer European. I'm not allowed in.
That's right. No, in the Olympics, this is a famous Olympic story. In 1992 in Barcelona or 96 in Atlanta, I can't remember which one. There was a long-distance runner named Boutayeb. And he was in this 10,000 meter race, and two other people, someone named Chilemo from Kenya, another one named Ska, I think from Morocco, were lapping. And this Boutayeb was a great runner. He had won a number of international competitions, but he was in the way. And you're supposed to move away.
Yes, you are.
As Chilemo and Ska were coming toward him, Ska was like, move, tell him, take the arm. And so he finally moved away. And what happened eventually was that Ska won and beat Chilemo. But then the event judges of the event took away his gold medal because they said that Boutayeb had helped him by blocking Chilemo. And it was quite the controversy.
Ooh,
and then what happened was it was reversed the next day upon appeal. But I remember watching that when I was a little kid, watching like that actual event happening on the coverage for the Olympics. And then he was showing Ska being so upset, but then
in every StarTalk episode, I have to do this, right? Charles White, how do you know that?
How do you know that?
Why do you know that? Okay.
Because
It's the
it
most
does.
random.
All right. So, Gary, I'm going with Charles's pronunciation here. Okay.
All right, I'm
Butayeb. Yes.
Yeah,
Yes.
Butayeb, and it's been phonetically spelt for us here. So here we go. If we imagine a thought experiment where two photons of light travel parallel to each other, one in the vacuum of space, the other in a fluid. They both travel at the speed of light, and by definition, their respective experience of time is zero. However, their relative speed being different, light moves slower in the fluid, they should actually have a different internal clock. How can we make that work as a question, or is there a mistake in this experiment?
Great question. It happens all the time, actually. And I want you to know that that's a great thought experiment, and it's actually a physical experiment that's been done a bunch of times. It happens when, for example, subatomic particles enter Earth's atmosphere. One subatomic particle misses the atmosphere and heads off into space. The other one comes into Earth's atmosphere and thus is going through the fluid known as the atmosphere, right? The compressible fluid of the gas of Earth's atmosphere. And what happens is that indeed they experience different
a fluid doesn't
times.
have to be liquid or wet.
That's right.
If a fluid takes the shape of its container, a gas would do that.
So it can be
Liquid would do that.
compressible.
So the whole field,
or incompressible.
fluid dynamics, the equations are the same that apply to the air or would apply to a liquid because of the dynamics that goes on for objects moving through it. Continue,
That's right.
Charles.
Yes, you're right. And so we have shown experimentally that the clocks for those subatomic particles that go through Earth's atmosphere actually run differently from the ones that are going off in space. And because of that, their decay patterns are different. Their half-lives are different as measured by us, not in the frame of reference of the particle. So this is an experiment that has been done, and there's some famous ones, specifically about a particle back then known as mu mesons. But you can
we don't
take
still
a look.
call them that? We don't still call them that?
Usually you just call them muons or mesons, right?
Oh, muons. Yeah, sure.
Yeah.
Sorry. Mu meson became muon. Thank you.
Yes,
Yeah.
that's right.
Yes.
So you can find these experiments and show that indeed the clocks of those individual particles differed from those of their companions that did not enter Earth's atmosphere. Yeah, great story.
Oh, by the way, the clock. So just to be clear, we're talking about particles traveling not at the speed of light. They have clocks.
Right.
But if you're actually traveling at the speed of light, you would not have a clock. And the question was about two photons, not about two particles.
Oh, well, in that case, what you do is think about it as having no clocks, but through different media. And so the speed of light will be different from one medium compared to the other. So you still have the same effect of causality of the surrounding environment having clocks. I hope that makes sense. I may not have explained it very well. But the idea is that if you're thinking of time and measuring time of that photon, which itself experiences zero time, the medium still affects the measurement.
So the speed of light is still the speed of light. The light is still traveling at the speed of light. It's just that stuff around it is slowing it to less than the speed of light.
Less than the speed of light in vacuum.
In the back.
Wait. So
less
Charles,
than the speed of-
something I learned only recently, because I never
Yes.
really thought about it.
Yeah.
That when light slows down in a medium, it actually doesn't slow down. What's happening is it's still moving at the speed of light between the particles that it encounters.
It just
Then it
keeps
has to
hitting
get
pieces.
through
Right.
Yeah.
Right.
And then it has to get through that particle somehow. It gets absorbed, re-emitted, or whatever if it's coherent. Because if the glass is translucent, then it's not a straight line through. And if it's opaque, it's not getting through at all. So the molecules have to be just right so that it is transparent to the photon. So it moves through where there's no particle at the speed of light, hits a particle, that delays it because it got to come out the other side to continue at the speed of light.
Isn't that just what Chuck said?
It is. But I wasn't going to say anything. Thank you, Gary.
I like your explanation.
That's exactly
Neil.
what I said.
I like both
But that's cool.
explanations. They're great.
Yeah.
I'm exerting
That's very
positive
cool.
consciousness.
Yeah. So the energy of the photon just had to get in and out of the atoms or the molecules that were in its way. But between them, it's still moving at the speed of light.
So it's getting refracted, it's getting diverted, it's getting,
all that can happen, and that takes time to get in and around the particles. But that's the energy moving, not a photon as a speed of light moving particle. So the point, Charles, is, and like I said, I only learned this very much later in life than should have been, that photons only ever actually move at the speed of light, even through a medium.
That's a great way to think about it.
I kind of see that. I can kind of see that.
That's cool. That's really cool. All right, let's get a little personal then. This is Michael Boisvert, who says, hello, Guardians of the Geeks.
Love it.
There's a t-shirt.
Guardians of the Geeks.
Michael here from Canada. Who does Charles Liu call when he doesn't have it?
Oh, no. Oh, no. Well, Mikhail, it's very kind of you to say that, but obviously I know much less than what I don't know. So when I need information, the first people I go to are obviously...
But you know much less than you don't know? What does that sentence mean?
It means that what I don't know far outstrips,
exceeds
on an infinite
what
level,
you do.
what I actually do know.
Gotcha. Except what you actually know far exceeds everybody else by an infinity.
No,
so they don't
Come
even
on.
know how to ask you a question in your infinity, because we're still embedded in our own infinity. Okay.
Dude, that's too much.
Okay.
Thank you. You're very kind. No, but when I do have a question, my go-to people, Mikhail, are Chuck Nice and Gary O'Reilly.
Oh!
You guys may not know this, but actually, Gary and Chuck, I wanted to ask you if you had a chance to take a look at my question that I sent you last week, where we would use the cross terms in Einstein's field equations to figure out the topological constraints to a many worlds interpretation quantum multiverse. Have you guys figured that out yet for me yet?
I wrote you back and I was like, what a dumb question.
Oh, I mean, you had it, right? I knew it. I mean, Gary, I don't know if you had a different opinion on that already.
No, I'm selling that to a really high-ranking think tanks at the moment, so I'm not prepared to discuss it in public.
Well, no, when Chuck Nice and Gary O'Reilly do not have a question answered for me right away, I usually go to my brilliant wife, Dr. Amy Rablew, and my 3 kids. I am blessed to be the dumbest person in my family.
I'm going to attest to that, actually, because I've hung out with this kid.
And so I always
his wife has a
count
PhD in mathematics. So
yes.
Charles is the dumbest one in the household.
It is true.
By far.
Order of magnitude. So Amy and the kids are really helpful, and I always go to them if I don't know something. And then if we all have to look something up, I always try to find at least 3 different sources with 3 different answers to compare them. There's so much misinformation.
Breitbart doesn't have your answer there, and Breitbart and Newsmax. And,
right.
For example.
And Fox
right.
News.
Really?
Yeah.
Exactly.
I always want to be sure. There's so much information out there that I estimate that a third of it is outright wrong, and a third of it is sort of right, and then a third of it is probably right. So I'm always trying to find at least 3 sources of information, people that I trust, sources that I know. I actually go back and read the papers if I can.
The original sources,
look at the actual pieces
but now
of information.
the real question there, though, Charles, because that can be flawed. I can look up 3 different sources, and they're not credible sources. Right. So how do you vet your source to make sure that it's credible? That's what I would want.
That is a process, and sometimes it's frustrating. It takes quite a bit of time. I will look at the source, and then I will look for references to that source and say, are those sources reliable or unreliable? What have other people said over long periods of time? Very often, if you type a search into any given search engine, the top 20 answers are all from the same source, but
they're just copies of each other,
spread out everywhere else.
Yeah, you have to make sure there's independence among.
That's right. So I don't hesitate to do that. It's a little bit of extra effort, sometimes a lot of extra effort to find the answers, but it's worth it. It's the way that I protect myself from misinformation.
So Charles is like the credible Hulk, who backs up all of his claims with research and documented peer-reviewed journals. That's the credible Hulk.
Smash! Shock! Dismember!
Okay, let's jump into the next question and we'll see. Because I think, you know what, it's a bit of a hot topic question, having looked at it here. This is from Jane Von Schilling from Scottsdale, Arizona. What are the possibilities of the combination of AI and quantum computers? So does this devolve into another question where is one more powerful than the other? And
they're both badass, and you put them both together.
And that's the end of us. Okay.
Or is that the beginning?
And that's all there is. No, you put it together, and that is the end of humanity. Say goodbye.
Or does that solve Charles's problems?
Let me tell you what the first. You know how like the first computers they had. Well, they were numbers, but they were for calculations. But the first thing that came out of computer was hello. All right, or the first
from the Macintosh. Yeah.
From the Macintosh. Hello. That was the first thing that came out of the computer. The first thing that will come out of a quantum AI computer will be, oh, you effed up now, didn't
you? It could be. But I'll say this, right? Our understanding of intelligence itself may, in fact, evolve dramatically once we understand how quantum computing and artificial intelligence merge. Ooh. It's really neat. Right now, remember, everyone, quantum computing is even in an earlier stage in its development than regular computing was in the era of those first counting machines that you were mentioning, Chuck. We are decades away from being able to do anything like put a quantum computer on your desktop, right? Maybe a century. Right now, the quantum computers are cryogenically cooled. They're the size of a room, and they're only able
it's a big
to do
hardware issue right now, not just software.
Tiny qubits at a time to make the calculations, right? But those tiny qubits can be extremely powerful, not necessarily because
just to be clear, a qubit is the quantum computing version.
Yes, thank you, Neil.
Bit
Yes,
that we'd otherwise find in a computer.
I should have made that clear earlier.
But that's why I'm here. Don't worry about it. Keep talking.
No, thank you. Yeah, a quantum bit, a qubit, right, is a thing that depends on staying coherent with other qubits in order to make its calculations. The quantum coherence is extremely fragile. It requires temperatures very close to absolute zero, almost no noise of any kind, electronic.
If you look at it the wrong way.
Pretty much.
If you breathe on it the wrong way.
Oh, yeah. It's all gone. So it's really, really in its infancy. But it shows a great deal of promise in the sense that when you put in 1 and 1, before it puts out 2, there's a lot of stuff in between which we can't see and happens almost instantaneously. And so is that a measure of how our own brains work? That's a great question. Artificial intelligence is our current human attempt to use non-quantum, classical physics to mimic our brains and our intelligence and our consciousness, right? And we're seeing that problem is almost intractable. To mimic a human brain, I saw a YouTube video on this recently. It is remarkably complicated. We know the steps, but the hardware is seemingly insurmountable in its difficulty. So those two things put together might do it, but we still got a long way to go before that actually
Charles,
gets to changing.
The insurmountable complications of the human mind might not be what you'd want to emulate at all. You want to emulate the parts of the human mind that are capable of good things and accurate things. The actual human mind, it commits violence and war and crime and genocide and all of this.
Not to mention that just the way that we perceive information is a perception. We don't actually view information; we perceive information,
sure.
which is a big problem.
After your senses dealt with it, right? So it's easy to praise the brain because we don't understand it, rather than ask, does the brain do things that we don't need to emulate at all because we can do it better by other means?
Well, let's first understand it, figure out what's actually good and bad and what's causing them all the interconnectednesses. And then we can distill the good stuff without worrying that will accidentally cause the bad stuff to happen.
And that's the frontier of neuroscience. But I agree with Chuck. Maybe AI will figure out how to perfect quantum computing.
And then how to perfect human beings.
Right? Together.
Will it not then, as you say, Neil, solve its own problems? I mean, look how long it took us from a computer the size of a room to get to a smartphone. That time is gone now. That won't take that length of time for it to solve problems that we think are impossible right now.
The issue is how we solve the problems.
And by the way, that's 60 years.
Right on the head.
Well within lifetimes, right?
Well, think about this. If we put an AI on the problem of solving climate change, okay, it might be able to solve it in a day. But how would it solve it? By killing every human being so that we don't have to create any more carbon. You don't want that kind of solution, right? That's the simplistic, simple-minded thing when you're saying, well, solve this problem quickly.
No, that's evil AI. That's the evil AI.
No, that's the AI that doesn't know the difference between good and evil.
Exactly.
That's the immoral AI.
The amoral AI.
Amoral.
So that's where that frontier is, I believe, Neil and Gary and Chuck. It's the issue of trying to make sure that we do it right and do it safe so that whatever AI doesn't ignore what we need of it. It's the other way around.
But if a human is in charge, if a human is in charge of AI and quantum computing,
so we tell ourselves,
right? Yeah. Well, let's go with temporarily in charge.
That's what you tell yourself about your cat. Yeah, I'm in charge of my cat.
Yeah, I mean, that's never ever going to be the case.
Right.
So the thing is, someone's going to have that immoral attitude and steer that intelligence in a certain direction. There's not always going to be Captain Good Cat in charge of AI.
And not everyone who's immoral believes that they are immoral. That's a whole other challenge that we have.
There you go. I mean, this becomes very ethical.
The winners of wars are those who write the history books. And so that's how that goes. And just to be clear, in case people didn't know, you can be moral or immoral. Amoral means you are neither moral nor immoral.
That's right.
So that's it. Just to be clear, people know how we use that term. Yeah. And so, Chuck, if you're an a-hole, are you neither one kind of hole or another?
Right. Well, no, if you're an a-hole, we know exactly what kind of hole
you are. I will wrap up by saying that, Neil, you actually know this much better than I do. Astronomers have been using AI and machine learning technology for decades. We have no fear of this material. We are perfectly understanding that this can be used to do great things, like help us understand data from millions of stars and galaxies when a single human being could do all that calculation at once. So it's not a matter of being afraid of it or saying, oh my gosh, we have to avoid it, or oh my gosh, we must exploit it. It's another mystery, a puzzle, a tool that we can work with and we can learn about and we can sick on our unknowns.
And if that fails, we all die. Okay, let's end on that note. Folks, we're all going to die.
Well, we'll all die eventually, right? It's just a matter of when and how. Yeah.
All right, guys. Charles, it's always good to have you.
It is such a pleasure to be here, everybody. Thank you so much for having me.
Rejoining us. And we know that when we all visit your house, we just say, where's the dumb one? I want to talk to him. That's going to be you.
Hands down.
Hands down. All right, Gary. Always good to have you, man.
Pleasure, my friend.
And Chuck Nice, you are in Aruba right now. Say hi to the Caribbean for us all.
Yeah, man.
Will do.
All right, this has been StarTalk Special Edition, its own version of Cosmic Queries. A delight in its complexity and its joy, especially brought to us in the guise of Charles Liu. I'm Neil deGrasse Tyson, your personal astrophysicist. As always, keep looking up.